Welcome to this explainer. Today, we're looking at micromechanical modeling of elastic short fiber composites. Now, I know that title is a bit of a mouthful, but we are unpacking a truly fascinating paper from the journal Composites Part B. We're talking about the verification of a brand new finite element-based orientation averaging method for short fiber reinforced composites. Short fiber reinforced composites, or SFRCs, are honestly absolute game changers in modern engineering. They give us incredibly high strength and stiffness compared to plain polymers, and they're quick and cheap to manufacture. But predicting exactly how strong or stiff they'll be, well, that is where the real challenge lies. Imagine trying to predict the stiffness of a composite material reinforced by literally thousands of tiny fibers. These fibers aren't just sitting in neat little rows, right? They're scattered, pointing in all sorts of crazy directions. Maybe they're somewhat aligned by the injection molding process, but largely it's just random. To truly understand the macroscopic behavior of this material, say how a car bumper made of this stuff will actually react to an impact, you've got to understand what's happening down at the microscopic level with all those individual fibers. The traditional approach is to explicitly model all of those fibers inside a representative microstructure and run a massive finite element simulation. This is known as using a representative volume element, or RVE. Notice the sheer complexity here. You draw a tiny 3D box, pack it with hundreds or thousands of microscopic fibers perfectly respecting the real-world volume fractions, build a highly intricate mathematical mesh over the whole thing, and basically ask a supercomputer to solve the physics. It's highly accurate, sure, but it comes with a massive headache. The problem is that these simulations become wildly computationally expensive. Plus, just generating realistic microstructures can be extremely difficult, especially when the fiber content is high. Okay, so let's dive into this specific bottleneck. When you have a high volume fraction of fibers, meaning lots of fiber and not a lot of matrix, or when the fibers are super long and skinny, the software literally struggles to pack them into the virtual box without them overlapping. Sometimes generating the RVE fails completely before you even get a chance to run the simulation. There's no way to work like that, right? So in this work, we introduce a new finite element-based orientation averaging method for short fiber reinforced composites. This is the core of our explainer today. Instead of banging our heads against the wall trying to build one impossibly complex 3D model, the authors of this paper proposed breaking the problem down into two much smarter, far more manageable steps. The core idea is simple, and I absolutely love it when incredibly complex engineering problems are solved with a conceptually elegant shift in perspective. So how do we actually get around the computational nightmare of explicitly modeling thousands of fibers? First, we model a single fiber embedded in a surrounding matrix using finite element analysis. We call this a unit cell, or UC. By isolating just one fiber and assuming a specific boundary around it based on the overall fiber volume fraction, we create a highly manageable, bite-sized simulation. We can easily mesh the single fiber and run precise loading conditions on it, like pulling it along the fiber direction, pulling it transversely, and shearing it. It's kind of like a giant puzzle, but we're just starting with one piece. This gives us the effective behavior of a representative unit cell. By running those simple tests on our single fiber model, we extract its exact elastic properties, its stiffness matrix. We now have a perfectly characterized mathematical building block. We know exactly how this single fiber, encased in its little block of matrix, will behave under any type of stress. Next, instead of building a massive microstructural model containing thousands of fibers, we statistically average the response of many unit cells with different orientations completely according to the actual fiber orientation distribution. And this brilliantly illustrates the power of statistics in mechanics. We take that single characterized building block and mathematically rotate it in 3D space to match the real-world probability distribution of the fibers in the composite. Then we just average all those rotated stiffnesses together. This creates an efficient and highly flexible two-step homogenization framework. Step 1, get the unit cell properties. Step 2, statistically average them based on orientation. It entirely bypasses the need to geometrically pack thousands of fibers into a single mesh. You can use literally any fiber aspect ratio, any volume fraction, and any orientation distribution without breaking a sweat. It's a real game changer. We also introduce a new self-consistent interaction model. Let's see how this builds on the concept. When you average the properties of all these individual fibers pointing in different directions, you have to make a mathematical assumption about how they physically interact with each other in the bulk material. I mean, they aren't just floating in a vacuum, right? They actually share stresses and strains. Traditional orientation averaging methods often rely on either the Voigt assumption, which provides an upper bound on stiffness, or the Reuss assumption, which provides a lower bound. Let me explain these bounds because they're absolutely foundational. The Voigt interaction assumes every single fiber experiences the exact same uniform strain, kind of like parallel springs. It's very stiff, the absolute upper limit. The Reuss interaction, on the other hand, assumes every fiber experiences the exact same uniform stress, like springs in a series. This is much more compliant, giving us the absolute lower limit. But reality, as always, sits somewhere in the middle. Our self-consistent approach bridges these Voigt and Reuss extremes by allowing each unit cell to interact with an equivalent medium representing the overall composite. So the crucial point is this. Imagine our single unit cell is acting as an inclusion embedded inside an infinite, homogeneous matrix. But here's the really clever part. We mathematically assign that infinite matrix the exact stiffness properties of the final overall composite. It's kind of like a chicken and egg problem, so the researchers solve it iteratively. They use a mathematical framework known as the Eshelby solution to calculate how strain concentrates in the inclusion, repeatedly updating the math until the properties of the equivalent medium and the final composite match perfectly. We validate the method against detailed 3D representative volume element simulations as well as experimental data. To prove this actually works, the researchers put it to the test against real-world materials like a polyamide matrix reinforced with glass fibers and a magnesium alloy reinforced with carbon fibers. They also went through the painful process of creating those massive 3D RVE simulations just to have a golden standard to compare their new, much faster mathematical model against. The results show that the proposed method accurately predicts elastic properties while completely bypassing extreme computational costs and practical difficulties. In the time it took to generate and run just one incredibly heavy RVE simulation, assuming the meshing didn't fail, of course, the orientation averaging method delivered highly accurate results in literally seconds. To put that into perspective, simulating 10,000 unit cells using this method took around 115 seconds on a standard laptop. The self-consistent interaction model in particular frequently nailed the actual RVE results right between those Voigt and Reuss extremes. Because the framework is based on finite elements at the unit cell level, it can naturally be extended in the future to include nonlinear effects like plasticity, damage, and fiber matrix debonding. Remember step 1? Because we're still using an actual 3D finite element simulation for that single unit cell building block, we aren't limited to just simple elasticity. Down the road, researchers can easily program that single matrix block to deform plastically, or program the interface between the fiber and the matrix to literally snap and debond under high stress. When you average that behavior out, you get incredibly rich, complex, real-world material failure predictions. This makes the method a very promising tool for efficient multi-scale modeling and engineering design of short fiber reinforced composites. You can check out materialslab.org for more on that. By replacing brute force computation with elegant statistical averaging and self-consistent physics, we open the door to rapidly prototyping entirely new composite materials right on our standard computers. It's a massive leap forward for materials science. Which leaves us with a final thought to ponder. If we can now accurately simulate the complex microworld of composite materials in mere seconds, what entirely new classes of lightweight, ultra-strong materials might we discover tomorrow? Thanks for joining me for this explainer, and keep questioning the world around you.